We've seen an example of functions in action, and we've worked through them all throughout algebra. But now we give sort of more of a general definition of what a function is. A function, f, which we'll denote as f in this particular case, between two sets A and B is a relation between A and B, okay? So a function is a relation, and what is a relation between A and B? Well, it's a subset of A cross B, or the Cartesian product between A and B. So it's a subset, but it follows a certain rule. This relation has to follow a certain rule in order to be a valid function. For every element in A, for every element which will denote x in A, there is a corresponding element in B such that the ordered pair xy is an element of that function. Okay, so think about f as a relation. It's like a capital R, but it has these two special properties. So let's analyze what this means. Well, if I take a look at an example, and I'll refer to this as set A, and you might remember this as the domain. The domain. And then over here I have set B, and as long as every element that's in an A has a corresponding element in B, then we've satisfied property 1. So we'll just put a couple of elements here, and let's say that this element corresponds to this element here. Maybe we'll call this 1, 2, 3, and A, B. Okay, so, and we'll also say that 2 points to A and 3 points to B. Okay, so what are all the elements in A? Well, A consists of the elements 1, 2, and 3. And to be in check with property 1, we need to make sure that every element inside of A is paired with some element in B. It doesn't say how, it just says every element in A must be paired with some element in B. Right? And so it is true because 1 is paired with A, 2 happens to also be paired with A, but the point here is that every element in A has a partner in B, and also the element 3 has a partner. Okay, so this is just for property 1. I'm not saying this is a function, I'm just saying that this meets the criteria for property 1. Now, there might be another example where perhaps we have the same domain. And by the way, B is actually called a codomain. We'll talk more about that later. Codomain and range are related, but B is actually called the codomain. And let's say that we have these 3 elements again, 1, 2, and 3. These elements here, A and B. But let's suppose that instead that 1 maps to A, and we use that word maps to a lot of times in mathematics, maps to, and we'll say that 2 maps to B. Well, for property 1, we require that every single element in A, of which there are 3, right? Element 1, element 2, element 3, has to have a partner in the set B. But we have a problem because the element 3 does not have a partner, right? It does not map to anything, and so 3 is not paired with any element in B, and therefore this violates property 1. Okay, so far, it might be the case that this relation right here is a function, but let's look at property 2. Property 2 states that if you have 2 ordered pairs that have the same input, and the first pair has an output of y1 corresponding to x, and the second pair has an output of y2 corresponding to an input of x, then this will only be a function if y1 is equal to y2. So essentially what this says is that the only way to have two different ordered pairs with the same input is if the outputs are also the same. Now you might remember in algebra, this was the vertical, we called this the vertical line test. And essentially if we had a function that maybe looked like this, then this was not considered a function because, hey, you know what? This input right here actually has, if I draw a vertical line, has two different outputs. So here we'll call this x, and we'll call this output right here, we'll call that y1, and maybe this one we'll call y2. And we see that there is an ordered pair x, y1, and another ordered pair x, y2. But clearly, y1 is not equal to y2, and therefore this violates property 2. So in a nutshell, a relation is a function only if every input in the domain has an output, and also if the two different ordered pairs where the input is the same have the same output, then and only then is it a function. So if I come back and I analyze this situation here, this relation, the first one we considered, this would not be considered a function because although every element in the domain has an element that it's paired with in the codomain, this is a function, I apologize. This also satisfies property 2 because every input actually only has one line extending out to the output space, to the codomain. So the input of 1 has exactly one output. The input of 2 has exactly one output. Although it's the same output as the input of 1 has, it doesn't matter. It doesn't say that every output has to be unique to only one input. But every single x has a y and only one y associated with it. So even if I drew a second arrow out from the element 1 like this, you might say, oh, you know what, that has two arrows coming out of it, so it has two outputs, but it's actually the same output, right? One goes with A for the green line, one goes with A for the blue line, and it is true that this element and this element are the same. And as long as that's the case, you're good. Now, an example of a non-function would be if, in where we still meet property 1, but we fail property 2, is let's say we have these elements 1, 2, and 3, and these two elements A and B. Suppose we had something like this, where 1 mapped to A and 1 mapped to B. Well, already you know that's not going to be a function, even if property 1 is satisfied. So now we see that every single input is paired with something in the codomain. So property 1, we're good. Every input has an output. But property 2 fails because 1 is linked with A and 1 is linked with B. But A and B are clearly two different elements in that set. Alternatively, we could meet, so this is not a function. You have to meet or obey both properties. And it's also possible to fail property 1, but be good on property 2. So same three elements, and same two elements over here. But suppose that 1 maps to A, 3 maps to B, and I think that's actually what we had, close to what we had in our second example. Now notice that property 1 fails because there exists an element in A that does not have a buddy in B, or is not paired with something in B. So property 1 fails, therefore it's not a function. However, property 2 we're good on because it states that if there's an element in A that has 2 arrows extending from it, both of those outputs have to be the same. So it's kind of like back up here where I drew the 2 arrows, but they point to the same output, and that was still a function. So property 2 we're good on. However, this is not a function because of the fact that not every input has an output. So not only does every input have to have an output, it has to have just one output. And that output does not have to be unique to that one input. And so back up here, we did have a function. And this is not a function for the same reason as in our final example here.